So, good day everyone. I am Rian Bibatong and my report is all about Schrödinger. So, Erwin Schrödinger achieved this goal in 1925 when he developed his Schrödinger equation, which incorporated the de Broglie relation. Erwin Schrödinger was recognized as the father of physics. Schrödinger is an Austrian physicist who ignited the debate quantum physics. In the early 19th century, Schrödinger created a new theory of quantum physics, which began an argument. In the late 19th century, he created his wave mechanics to prove that his theory was correct. This essay will seek to cover Erwin Schrödinger's early life, which leads him to a major discovery, such as the creation of quantum physics theory, the invention of wave mechanics, quantum physics forever. This is the differential equation which utilizes concepts in mathematics that are beyond the scope of this series. But we can certainly discuss the conceptual implication of the equation. Essentially, just as F is equals to ma applies Newtonian systems, the Schrödinger equation applies to quantum system by describing the system a three-dimensional wave function represented by the Greek letter psi. So in this equation, the H stands for a Hamiltonian operator, which is a set of mathematical operations that describes all the interactions that are affecting the state of the systems, which can be interpreted as the total energy of a particle. But while the Schrödinger equation can calculate the wave function of a system, it does not specifically reveal what the wave function is. Max Born proposed that we interpret the wave function as a probability of amplitude, where the square of the magnitude of the wave function describes the probability of an electron existing in a particular location. So, looking back at the double slit experiment, we understand the diffraction pattern as illustrating this wave of probability. The pattern is not the electron itself, it is the probability that an electron will arrive at each location on the screen. We can predict where one electron will go. Only the probability that it will arrive at a particular location. If many electrons arrive at the screen, it becomes apparent how their distribution obeys the wave function. So the Schrödinger equation does compute the wave function deterministically, but what the wave function tells us is probabilistic in nature. This idea that nature is probabilistic on the most fundamental level was a lot for the scientific community to handle at the same time, and still is for some. So, unlike the mechanical waves on a string or sound waves in air, the wave function for a particle is not a mechanical wave that needs some material medium in order to propagate. The wave function describes the particle, but we cannot define the function itself in terms of anything material. We can only describe how it is related to physically observable effects. So just the way sound waves are mechanical waves and light waves are oscillations in an electromagnetic field, an electron can be considered a cloud of probability density. So there are many such interpretations of quantum mechanics, which involves different ways of viewing the relationship between the wave function, experimental results, and the nature of reality, and there is still no firm consensus as to which view is correct, be it the Copenhagen interpretation, many worlds interpretation, or a number of others. These children are talking over a cup and string telephone. The displacement of the string is completely described by a wave function. In an analogous way, a particle is completely described by a quantum mechanical wave function. The Schrödinger equation is a linear partial differential equation that governs the wave function of a quantum mechanical system. Its discovery was a significant landmark in the development of quantum mechanics. So conceptually, the Schrödinger equation is the quantum counterpart of Newton's second law in classical mechanics. Given a set of known initial conditions, Newton's second law makes a mathematical prediction as to what path a given physical system will take over time. The Schrödinger equation gives the evolution over time of a wave function, the quantum mechanical characterization of an isolated physical system. The quantum can be derived from the fact that the time evolution operator must be unitary and must therefore be generated by the exponential of a self-adjoint operator, which is the quantum Hamiltonian. Introductory courses on physics or chemistry typically introduce the Schrödinger equation in a way that can be appreciated knowing only the concepts and notations of basic calculus, particularly derivatives with respect to space and time. So the form of the Schrödinger equation depends on the physical situation. The most general form is the time-dependent Schrödinger equation, which gives a description of a system evolving with time. So, where t is time and the state vector of the quantum system being the Greek letter psi, and h is an observable the Hamiltonian operator. So the term Schrödinger equation can refer to both the general equation or the specific non-relativistic version. The general equation is indeed quite general, used throughout quantum mechanics for everything from the Dirac equation to quantum field theory by plugging in diverse expressions for the Hamiltonian, and the specific non-relativistic version is an approximation that yields accurate results in many situations, but only to a certain extent. So, see the relativistic quantum mechanics and relativistic quantum field theory. So, to apply the Schrödinger equation, write down the Hamiltonian for the system, accounting for the kinetic and potential energies of the particles, constituting the system, then insert it into the Schrödinger equation. The resulting partial differential equation is solved by the For the wave function, which contains information about the system. In practice, the square of the absolute value of the wave function at each point is taken to define a probability density function. Once again, thank you for watching and listening.